So remember yesterday we ended a little bit on a cliffhanger, and I want to remind everyone what that cliffhanger was, and then we can resolve it. So we were using MMD as a critic in a GAN, okay? So the critic is something that takes a bunch of fake images that my generator made, takes a bunch of real images that are reference images, and compares them and says, are these two sets from the same distribution or not? So this is my grumpy-looking critic here. And remember how we did this. We took these images, we passed them through some convolutional neural nets to extract features from these images, and then we used the MMD, the maximum mean discrepancy, to compare these transformed images. And the MMD is a measure of distance between sets of objects, so if that MMD is very small, that means the sets are close to being from the same distribution. If it's very large, then it's unlikely to be from the same distribution. So the question became, well, how do we train these convolutional features to extract useful properties of the images that we're comparing? Now we remember that maximum mean discrepancy is an integral probability metric. So that's something that finds a smooth function which has large positive amplitude, in this case on my real points, and large negative amplitude on my fake points. And so if this function is perfectly flat, then my real and fake points overlap. If the function is got like bumps in it, as it does here, that means that my red and my blue points are far away from each other. And then we wanted to modify this function in a bit, like in a sense weaken our MMD to make it easier for the GAN to learn. The original plan we had was to make the gradient close to 1 on this line. But then if you remember yesterday, we found some problems with this approach. And so then we skipped ahead a little bit and we said, well, let's take the approach here, which is that here is my witness function, and I want my classifier, my MMD, my discriminator, I should say, to be reasonably invariant to the kinds of, variety that we see among the blue points. So as I move among my population of dogs, I want my witness function not to change too much, because this is the variability that I expect in my real data. Now, this is a weakening of the critic function, because I'm telling it to ignore certain transformations in my data, to ignore certain directions. But this is a meaningful weakening in the sense that these are the invariances that I expect to occur within the data set that I'm matching. Okay? So I'm saying let's force my witness function to be flat around the support of my real dogs, and then away from that it can be steep. It can let my my generator learn to climb this hill until it gets to the top. All right? So this is where we got to, and we thought, oh, this might be a good idea. Then we expressed it in math. So here is my perturbed maximum mean discrepancy, where I've said I'm looking for a smooth function f, which is maximizing my difference in expectations, EP of f minus EQ of f. All right? And then I've got this constraint, which I've done a little box around, and this is a combination now of 3 different constraints. The last one that you see in the set was the constraint that my function should be smooth in a generic sort of off-the-shelf sense. But then I've got 2 extra terms, and these terms are the ones that enforce that my function doesn't change much over the support of my p. So in particular, this second term says that the gradient of f in expectation over the support of my p should be small, okay, which means my function is going to be flat over my support of p. I need the L2 norm, this variance constraint, because if I'm constraining my gradient alone, that's not enough to specify my function. I also need to say something about its amplitude, not just its slope. All right? And we were very optimistic about this, and we thought, oh, we'll code something up. It's going to beat everyone. Didn't, because it's just way too slow. So this was the cliffhanger. So if you look at our NeurIPS paper, you'll see the math to implement this. It's solving a linear system. Linear systems cost cubic in the number of samples to solve. That's really expensive if you're doing it in many iterations when you're training your GAN. So this was a dead end, sad to say. So the resolution of this cliffhanger actually turns out to have been very simple. What we did is we just defined a new MMD as a scaled version of the old MMD, where in this expression here, we're making the constraint on the gradient and on the L2 norm, on the variance, not of the function itself, but of the features that define it. So this term here is the variance of the features on x. The final term in that expression is the expected derivative norm of the features on x. And so basically, like I'm saying that the norm of the slope of the features shouldn't change much over p, which is almost as good as saying that the slope of the function shouldn't change much over p. So this expression here turns out to be very cheap to compute, and it has the same sort of smoothing effect in the sense that if I'm defining functions of these features, and I'm saying that my features should have derivatives that don't change much over the support of p, then the function that I define in terms of these features will have that property as well. So the function's derivative won't change much over the support of p. So this is something we've proved in the paper. I'm explaining this at a sort of qualitative level here. You can check the details in the paper, but the idea is what I've just told you. Is this idea clear, or are there questions about it? So I have a function of features. I've said that, initially I said that the derivative of that function, the slope of that function, shouldn't change much over the support of p. The function should be flat. Or sorry, I should say the derivative is small over the support of p. So the function should be flat. Now I'm saying, well, it's a function of features, so that means if I say the derivative of my features should be small over the support of p, then I take a sum of those features with some scalars, then the function will inherit that property. Yep? Okay, so that's a very good question. So first of all, which is the model, which is the data? So I'm always using blue for my real points and red for my fake points. So then if I write here Q in red, Q is always fake because it's red. And yeah, I forgot to say that, so good that you caught me. The other question is, like, I'm requiring that my function should be flat around the support of my real points, but I haven't enforced anything on my fake points. So the reason is that I don't want my functions to be invariant to the kind of like crazy stuff that my generator might be doing. So my generator might be, it's generating a set of points, and I might say, well, why don't I make my function flat across the variability of my generator? The reason we don't do that is because this variability is an artifact of our generating network. It's not a property of the images that we're trying to generate. And so we don't want to make our function try to adapt itself to properties of our model. We want to train our model, not like give it a free ride. So I mean, in practice, it seemed not to actually matter that much if we added a flatness term here. There are arguments for it, which basically rewrite this GAN training as a solution of a differential equation and argue that flatness there makes sense for that reason. But I personally don't believe that it does. Yeah. It turns out that I can add a penalty for the flatness there. It just slows it down, but it doesn't kill it completely, probably because there's enough gradient left over from other sources, yeah. Are there any other questions about this notion? Yep.
I just want to ask, in this framework, does it behave differently to the gradient penalties proposed by Schroeder in the, which GANs actually converge?
Yeah, so... Mm-hmm. Yeah, so the gradient penalty for the FGANs actually has a slightly different justification and purpose than the ones here. So if you remember, the FGANs are you've got an F of a ratio of P to Q. If P to Q have disjoint support, the ratio is infinite. So, that's a problem. The way that people get around this is, in a sense, by adding noise to your sample so that the support always overlaps, so the ratio is not infinite. The gradient penalty in the FGANs is a numerical approximation to this process of adding noise. So the purpose of the gradient penalty in FGANs is actually quite different to the purpose of the gradient penalty here. Yeah. Okay, so this is what we're doing. We're making our function, well, we wanted to make our function flat across the support of the blue points. We can't do that, but what we can do reasonably cheaply is to say that the gradient of the features that define our function should be small across the support of the blue points. The function then inherits that property, and we get a function that's flat across the support of the blue points without the terrible cost of the original formulation. So this is what we ended up doing. So let's see now. we're regularizing the features directly. We're making the gradients of the features directly small over p. Okay, so now let's see how well it works. So the question of how well it works is a very, I guess, tricky one in the GAN community. I don't believe there is an answer yet. I'm going to propose an answer that at least fixes some of the bugs of earlier answers, but for sure it's not the final say. So the, I guess, earliest classic means of evaluating a GAN is called the Inception score. What you do is you train a classifier on your, I guess, domain that you're working on. So if you're using CFAR, you want to train a classifier on CFAR. And you use this classifier to compute a score here. So y is the label that your classifier gives an x. And what this expression does is it sort of requires two things. It requires, on one hand, that the predictive label distribution y given x is low entropy. So you're very confident when you see one of your generated samples that it's a dog or a car or a tree. The other thing is that I want my label entropy to be high, which means that if I have dogs, cars, and trees, I want to generate all of them. I don't want to just generate trees. Okay, so that's the Inception score, and it seems like a reasonable idea. The downside is that it relies on a trained classifier. So, if your GAN is being trained on a domain when there are many classes and you're going to learn to generate samples across each class, then this is probably a reasonable thing. But let's say you're generating bedrooms or celebrity faces, and your classifier is just saying like bedroom, bedroom, bedroom. I mean, that's not a very interesting thing. People have, I think, used Inception, or misused Inception in that context, but that's, yeah, none of you will do that, of course. So then a paper following up on this did something which I think is quite a bit more interesting. It's called the Fréchet Inception distance. So what you do, you use the pool 3 layer of the Inception architecture as your features. Then you pretend that the distribution at that pool 3 layer of the features of your real and fake points is Gaussian. And then you compute a Wasserstein distance, Wasserstein 2 distance, I think in this case, between your real and fake Gaussians. And that's what this expression is here. So it says the means have to be close, and the dot product of the covariances has to be close. So that's what this is doing. So this is the Fréchet Inception distance. So there are two questions that you might ask about this. So one is sort of the obvious question is, are these features really Gaussian distributed? Probably not. But there's actually a more subtle and I think more fatal flaw with the FID, which is bias. So here is an illustration of bias. In the plot that you see here, on the x-axis I've got number of samples, and on the y-axis I've got FID. Now this is FID between like what are notionally real and fake samples, but in this case I've actually taken real samples for both P and for Q. So this should be 0, but it's not, right? And what you see is that the value of this FID is quite far above 0 and is dropping to 0 reasonably slowly. So I've used 10,000 samples and it's still pretty far from 0. So this is an illustration of bias. What I'm seeing is that this FID, the value of the FID that I see depends on how many samples that I've compared. So if I have an FID that I've computed on 4,000 samples, then someone could beat me by just using the same algorithm with 10,000 samples. So if the score that you get depends on how many samples you've seen, that's probably a little bit sketchy. So this, bias property actually has another. I mean, I can illustrate it in two more ways. One is that you can construct an example such that the FID always gives you the wrong answer, and it's a very simple example. Okay, so let's say that I've got these two P's. Okay, the P1 is a normal distribution with a variance that depends on M. So M is the number of samples I've seen, and so I'm changing my variance as I see different numbers of samples. And P2 is standard normal, means 0 variance 1, and Q is standard normal, means 0 variance 1. So let's look at this. Well, obviously, which is the better model for Q? Well, it's P2, because it's the same, right? But if I compute the FID between P1 and Q, so if I compute the FID between P1 and Q, like the true FID, it's 1 on m squared, which is always bigger than FID of P2 on Q, which is 0. But let's say now that I compute these FIDs, not not in population, but just based on samples from P1. So in this case, in expectation, the wrong model always gets a lower FID than the right model. So the bias just corrects for the fact that FID1 is 1 on m squared and basically breaks it. So bias means that I always prefer the wrong model over the correct one. So this is a toy example. You can see the proof in our paper, how we did this. But this is kind of annoying because it's saying my FID is always telling me the wrong answer no matter how many samples I've seen for this example. So a reviewer criticism of this might be, well, this is a really toy example. You've just constructed these two Gaussians. One has just the right variance, and you've shown FID is wrong. But what about in something more realistic? Is it still the case that FID can hurt you? So the next slide is that the FID can also give you the wrong answer in practice. So let's generate some sort of reasonable neural network output-ish distributions. So P1, I'm going to just pass a normal through a ReLU. P2 is I'm going to pass another normal through a ReLU with a slightly skewed covariance. And Q is going to be a standard normal pass through a ReLU with mean 1. Okay? So these outputs are at least outputs that you might expect to see from a neural network with ReLUs, even though I've only used a single layer here. So in this case, I'm going to randomly draw my covariance of P2. It's going to be a sort of skewed covariance. And FID for P1 is going to be bigger than FID for P2. Okay, so this is what with infinitely many samples, P1 is the worst model. But if I give it just 50,000 samples, P1 is a better model. But then if I give it 100,000 samples, it switches order. So this is a case where it's not only the absolute value of the FID that depends on how many samples you've seen, but the ordering of the preferred model can also switch. So if you've seen too few samples, you might prefer the wrong model over the right one. So, this is not a systematic bias where one model is always preferred over the other. It's a bias where the model that's preferred depends on how many samples you've seen. So again, if you're comparing models and the answer you get depends on how many samples you've given it, then you would sort of question the validity of that as a model comparison. Okay, so this is, the issue with FID. It has a bias, and the bias can mislead you by giving you the wrong answer if you give it the wrong number of samples. The way that we've attacked this bias is by using something we call the KID, the kernel inception distance. We use exactly the same features as FID. We use the pull 3 layer of Inception network. But we compute just the MMD between the real and fake samples using a third-order polynomial kernel. So this is something that checks the match of the means, the variances, and the skewness, so the third moment. And what you can see here, I've done the same plot that I did for FID before, but now with KID. So I've got n, the number of samples is going up on the x-axis, and I've got on the y-axis the KID. And this is between CFAR and CFAR. So my real and fake samples are both real. And you can see here that the variance is decreasing as I see more samples, but the mean is 0. So there is no bias here. So KID at least resolves the problem of bias. So there may be other limits, like y pull 3 layer of Inception, y third order kernel, like these questions that are valid, which are directions for further research. But at least we've got rid of this annoying bias problem. So the KID score is the one that we're going to be using in our experiment. So there are questions about this before I go on. Okay, good. So this is I think the way to evaluate. I should also say, people might argue that this KID score is computationally costly because it's quadratic in number of samples. The way we've implemented it, actually, it's not, because what we do is a sort of block estimate of KID. details are in the paper, but basically it's sort of linearly scaling in the number of samples and quadratically in the number of elements in a block, which you'll see in the code. So we've got this also in TensorFlow, so you can use it right away. It's in TensorFlow contrib, so just go ahead and run it, basically. The other thing we use this for is learning rate adjustment. So as you're training your GAN, at some point your improvement stops happening and you want to drop your learning rate. So you can either do that by like eyeballing it, or you can check if your kid is significantly improving, from one time to the next. And if it's not, you drop your learning rate. So this is actually how we have an automatic tuning of our learning rates when we're training our GANs. This is how we do it. All right. So now we do the benchmarks. So this paper I mentioned yesterday, it appeared in Eurips. So for that reason, we had to compare against all of the iClear papers from the same year. We compared against this spectral normalization GAN, which was, I think, a really good GAN from that year. We compared with Yoshua Bengio's group, this boundary-seeking GAN. We compared with Sobolev GAN, and we compared with our own previous ICLR paper, which was doing this slightly less principled gradient regularizing strategy. So one of the things that I mentioned yesterday is, in a sense, like, what do you gain in using kernels on convolutional features versus just using the convolutional features and using linear combinations of them as our witness function? So this is something I'm going to illustrate here using a sort of ablation approach. A little bit hard to see what's going on here, so you might want to check my webpage later, but you'll be able to see, I think, pretty well what's going on. So in this case, the critic features we're using are the DC GAN critic features, so we're using off-the-shelf critic functions. And the F parameter tells me, in a sense, like how complex are my critic network, our critic layers. So larger F means I'm using more features. So in this case, I'm generating bedrooms. And I've got my bedrooms with the Wasserstein GAN, which is basically using a linear combination of the critic features. And I've got my bedrooms generated by MMD GAN, which uses the critic features and then puts a kernel on top. And what you're going to see here is that the difference is pretty much a wash. There's not really a difference. So it seems we may have wasted our time. But now let's simplify the critic network. Okay, so here I've used F64, which tells me the size of my filters. Now let's use 16, much smaller critic network. And you'll see here that like the KID for MMD GAN has gone up. I'm using a smaller critic network, it's less powerful, but the bedrooms are not catastrophically worse. The WGAN, the KID has gone up to 37. And you can even see, like, even on this screen, you can see that like you're getting these blurred like blobs of unconverged something. So basically what you get when you're using the kernel features on the convolutional network is some features for free that you don't have to train, which means you can get away with simpler critic networks. The training is also more stable because there's a bunch of features that are already converged that you're using. So this is, in a sense, like the purpose of using these sort of hybrid networks where you've defined your kernels on your convolutional features. All right. So now everyone who does a GAN talk has to do celebrity faces. Here are our celebrity faces. Bear in mind, like, each of these can be sold for $400,000 at Christie's in London. So you're seeing like a really expensive slide here. The other thing to notice, we're getting a lower KID score. We're also getting lower FID scores because like people like to see FID, even though it's sketchy. But here we just show our KID scores are better than these competing methods. Of course, since Eurips, like there are new papers that have been submitted to iClear next year, which use even better, architectures and training approaches. So as always in machine learning, everything I show is out of date like the next day, but these were pretty good. We also trained on unconditional ImageNet. So ImageNet is a very tough data set because the number of classes is very large. It's 20,000 classes, and the image, like the size of the data set is very big. So often when you see ImageNet examples, what people are doing is they're training a conditional GAN. So they're saying like, given that I've told you I'm going to generate a dog, generate me good dogs, or generate me good cars, okay? In this case, we're not giving it any label information. We're just saying, like, generate me a picture of something that occurs in the world. So this is a very tough problem. And I think, before iClear last year, I don't think anyone had really trained successfully on unconditional ImageNet. In iClear last year, a couple of papers managed to do it. We also managed to do it using this and to get, I think, better KID scores, better FID scores. So this is, I think, it's a very tough problem that illustrates that you can still get a convergent and, visually plausible generator using the gradient penalized MMD GAN on a very, very tough data set where, it takes a long time to train, it's very tough to train, but it's working. Yep. Mm-hmm. Yeah, so in fact, we could use the MMD. So first of all, you can't, if you define just MMD in terms of generic features on images, probably not a very good idea because it doesn't prioritize the features of images that are, in a sense, useful. It'll find a difference. It'll say, with absolute probability 1, these are different. But it's not a meaningful number because it'll say that for everything. So one could define the MMD on the pull-3 layer of the Inception network as well, using an exponentiated quadratic kernel. We didn't do that more for psychological reasons than for mathematical reasons. So we were afraid that the reviewers would think that we were, using our own criterion to test our method, and so we didn't do that. I expect, though, that by the time you've taken into account mean variance and skewness, you're probably capturing most of the interesting properties of the distributions at the pull-3 layer. I don't think it's like crazy multimodal or anything like that. Any other questions about this? Okay. These are the images of BGAN, the boundary-seeking GAN. It does occasionally some weird things, like it has these uniform fields of color now and then, but like it's pretty good as well. And the spectral normalized GAN also does pretty good things. So from a human viewpoint, particularly at this resolution, there's not a lot in it, but we are getting, I think, quite a bit lower scores. So I think we're covering the support a bit better than the competing models. Okay. Just to let you know, the KID score, it's implemented in this library. It's also implemented in TensorFlow, so it's easy to use. We also have the code for generating these gradient regularized MMD GANs online as well. So you can run all this stuff yourself and check that we're doing what we said we're doing. So I encourage you to do that and get some nice pictures that you can sell. Okay, so this is everything about training generative models. Are there questions about this before I go on? Yep.
Is it possible to directly just optimize the kit score?
You can, and it's probably not going to be a great idea because you're using these pre-baked Inception features. So we found that having features that adapt to the data that you're trying to learn is a better approach than using pre-baked features. One of the earliest MMD GAN papers from 2015, the one by Rich Themel's group, was using pre-baked features and was getting better results than, defining a kernel directly on the images, but having adaptive features is better again. It's not going to be it won't be a disaster, but you will do better with adaptive features. Okay. So let's get rid of this, and we will go to the next one. So in part 2, there are actually 2 parts. There is going to be, I've got 2 sections. One is comparing models and samples, so how good is my fit of my model, and the second is detecting dependence. What I'm going to do is I'm going to start from the second part, because I think that one is probably a better one to do. And then if we get time later, we'll return to the goodness of fit for models thing. So I'm going to stick with this one first, okay? Good. So testing statistical dependence. So here is the example that we started the previous talk with, okay? We've got a pair of observations. We see observations in pairs now. And we see two things. We see an image and we see a caption, okay? Now, you know, what we can detect as humans is that the images and the captions seem to be related. Like if I look at this and I see like a responsive interactive pet that blows in your ear and follows you everywhere, and this thing, like, it seems plausible that these are related, though I don't have cats, so I'm not sure. So what we want is an automated means of detecting whether these dependencies exist, whether the image and the caption are dependent, but we don't want to solve the harder problem of mapping from one to the other, okay? So in particular, like, you know, these captions don't say, like, this animal is brown, it has 4 legs, a nose, and a tail, right? It's not something that's easy to regress to the image from. So in a sense, you know, the caption depends on the image, but in a way that's actually rather subtle and which would require quite a lot of learning to determine. That's a hard problem. We don't want to solve a hard problem. We just want to know if these are dependent without solving that hard problem. And it turns out that this is possible. It's a little bit surprising that it's possible, and I'll explain to you why. All right. So immediately, because you were in the lecture yesterday, you might think, well, if I'm trying to detect dependence, can't I just use MMD? And in particular, can't I use MMD between the joint distribution, Pxy, and the product of the marginals, Px times Py? Because if Pxy equals Px times Py, then indeed the variables are independent. So that seems like a very short lecture. I've solved the problem. We can go on. There's two little, I guess, flies in that ointment. So the first one is, like, I don't actually have Px times Py. Okay, I'm only given a sample from the joint. I'm not given a sample of the product of the marginals. So the answer to that is actually a really short answer. I can simulate it. So I can take a picture and I can add a random caption to it. I just choose from my set of captions a random one, I add it to the picture. Suddenly they're independent. I know they're independent because I constructed it that way. Okay, so that solves this problem. But there's a harder problem, which is what kernel do I use, right? Because I need some kernel that measures how similar one image caption pair is to another image caption pair. So I have my image and my text, and I'm saying how similar is the image and text to a second image and text, right? Because the kernel is a measure of similarity. And this is hard, right? I might have a good measure of similarity for pictures, but for combined pictures and text, like that's, you know, there's not an obvious answer to that question. All right? So I will give you one answer to that question. Okay, let's say that I've got a good kernel on images. So this tells me how similar my pictures are. And let's say that I've got another good kernel L on text. Okay, so individually I have how similar are two images and how similar is one text to another. So a valid kernel between one image caption pair and a second image caption pair is just the product of the kernels. So a way to understand a product is a sort of AND operation. If both of them are large, then the product is large. But if either is small, then the product is small. That's a sort of very high-level way to understand it, but I find it helpful to think about it. So this is a valid kernel. The sum of two kernels is also valid. So if I sum my kernels, that would also be a valid kernel. So this is a pretty arbitrary choice. I haven't justified it. I'm going to just use it. But I'm going to, in the course of the lecture, I'm going to explain to you why this is not just an arbitrary and random choice, and why it's a preferred alternative over other ways to combine these kernels. Okay? So now let's say that I've used this product of kernels. This is my choice of kernel for whatever reason. Then it turns out that the MMD between the joint and product of the marginals is the trace of the product of the K and the L matrices. So the K is the matrix of kernel values between each pair of images, and the L is the matrix of kernels between each pair of captions. Okay? So this is now my MMD. If I'm using this product kernel, that's the form it takes. So how do I interpret this? So here's a nice way to think about what this means. Okay? Here is my K matrix. This is how similar every pair of images is. And you'll notice that like two dogs have a higher similarity than a dog and a cat. Okay? And let's look at the L matrix. So here, the two dog descriptions are more similar than the similarity between the dog description and the cat description. So what you notice is that a pattern that occurs in the K matrix also occurs in the L matrix. Similar objects in one view are also similar in the other view. And different objects in one view are also different in the other view. So if this pattern occurs again and again in the K and L matrices, then we could conclude that the pictures and the captions are related. Because if a pair of images is similar, then their captions are similar. If a pair of images is different, then their captions are different. How do I determine how similar these two matrices are? I just take their matrix dot product, which amounts to sort of unrolling both matrices, treating them as vectors, and then taking the vector dot product. And that's what this trace of K times L does. So this is actually, a reasonably simple thing to understand. And what's more, at no point did I have to regress from my images to my captions. I only looked at the similarities within the image space, the similarities within the caption space, and then I took the dot product of these two matrices of similarities. So is that clear? Okay. So, yep. Yeah, so this is a very good question. Like, could I be missing something here? The answer is, if you remember the terminology from yesterday, characteristic kernels, these are kernels for which the mapping of a distribution is unique. If I use a characteristic kernel for my K and a characteristic kernel on its respective domain for my L, then I can guarantee that this will be 0 if and only if X and Y are independent. Yeah. This is a consequence of using this product kernel. There are other reasons to use the product kernel for interpretability and so, but yeah, this is one of the advantages of that. Are there other questions? Okay, so we've discovered a way to show whether X and Y are independent without having to regress from X to Y. The problem, I think, with such a criterion as I've presented it is that it's very hard to interpret. So like, if I'm a scientist and somebody asks me, well, is this signal that I see dependent on my brain activity, or does my brain activity depend on my signal? And I answer, well, I computed the MMD between the joint and product of marginals using these kernels, then they might look at me really hard and then ask someone else. So I want something that I can interpret. I want something as powerful as this, but that I can understand a little bit better. So let's think about what that might look like. Okay, so first of all, why the product kernel? I've actually answered a little bit that question already, but the more interpretable way of defining the dependence measure is also very important. So, here's what you would see in a Statistics 101 textbook if you're thinking about dependence. And in this case, what you would be thinking about, or the way it would be introduced, is in terms of linear correlation. So here I've got my x on my x-axis, my y on my y-axis. I've seen a scattering of points. Each of these points is an xy pair. Each of them is drawn independently, but you can see a nice linear trend. And then I compute my correlation. It's very large. If I compute the p-value, it's very small, and I conclude that there's a statistically significant dependence between x and y. The problem with this is that correlation is not dependence. Dependence is much, much richer than correlation. All right? So here is an example of variables with a correlation of 0.07. My p-value is like, way, way in the wrong place. Okay? But yet, visually, you can see that x and y are very dependent here. And they're dependent because the variance of y depends on where x is. So in the middle of the plot at around 0.6, the variance is tiny, it's collapsed. At the edges of the plot, it's bigger. So obviously, where x is tells me how big my variance is, and yet the correlation is 0. So if I just blindly run my statistical test of correlation, I'm going to conclude that there's no dependence, even though the dependence is really strong. So I've missed this, and that's a problem. What about this case? So here, x and y are in a nice little ring. The correlation is 0, and yet x and y are really dependent because, where x is has a very big influence or very big dependence on where y is. And yet, again, I run my standard statistical test off the shelf. I'm going to get no correlation. I'm going to conclude they're independent. They're really not. Okay? So I want a way to, in a sense, find dependence in these cases in a way that's interpretable and that's also sufficiently powerful, that I'm not missing anything. So how could I do that? All right, here are my x and y. They're very dependent. They're not correlated. Now I'm going to map my x variable through a smooth function and my y variable through a smooth function. All right? So these smooth functions I've just plotted here. They look a little bit arbitrary, but when I map x through its smooth function and y through its smooth function, I'm getting variables that now have a very high correlation, 0.9. Okay, very significant. So a more general way to think about how to characterize dependence is I could say not is there a strong linear correlation between x and y, but if I map x and y through a simple mapping, I map x through a simple function, y through a simple function, do I get strong linear correlation? And that's a more general notion of dependence because I'm allowing my variables to transform so that I can get strong linear covariance. But I'm restricting my class of transforms. If my transforms were arbitrarily non-smooth, I could make my variables line up in a perfectly straight line, no matter how independent they were. And that would be useless. So I need my transformations to be simple. And I think this is much more interpretable, because if somebody asks me, are x and y dependent, and I say, well, if I map my x through this smooth function and y through that smooth function, my correlation is really, really significant, then that's something that's interpretable. Like I know a transformation of my data that's like simple, that's reasonable, and which causes those to be linearly dependent. So, you know, to my mind, this is a very like interpretable dependence measure, which is also general, because I'm not only detecting linear correlations, I'm detecting nonlinear dependencies as well. Okay, so since I now need two classes of functions and they both need to be smooth, how do I define these two sets of functions? So here we're going to do a flashback again to yesterday. Yesterday I just had one function for MMD, right? I said I had a function which is a sum, a weighted sum of features, okay? These features become less and less smooth as I go down the list, and their amplitudes get smaller and smaller. So if I take a weighted sum of these features, I get a smooth function. Okay? And if I'm doing an algorithm with these infinite feature dictionaries, as long as this algorithm only uses the dot product of these features, I never need to write them all down. Okay? So my class of functions f that transform my x are going to be linear combinations of smooth features of x, just like this. And I will also have a second function g, which will transform my y variables, because now I've got x and y. You'll notice that those features have the same property as the features on this side. They become more and more rough as I go down the list, and their amplitude gets smaller and smaller. But the shape of the features isn't the same. This is because, you know, why should I use the same features on my x and my y? Maybe I will in some cases, maybe I won't in the cases, for instance, where I have images and captions, and the features are completely different. So I've got functions of features of x, functions of features of y. These are the smooth functions that I'm going to use here and here. But, you know, unlike MMD, I've got now two functions, one on my x space, one on my y space, rather than just a single function as I had for MMD. All right, my two classes of functions. Now I'm going to define something called the COCO, the constraint covariance, where I'm saying that I want to maximize the covariance between f of x and g of y, subject to these functions being smooth. So my f should be in the unit ball, the g should be in the unit ball. What does that unit ball constraint mean? It means that the sum of the fj squareds has to be less than or equal to 1. The sum of the gj squareds has to be less than or equal to 1. If these two constraints hold, then you know this thing is correctly defined. And this is actually what I'm plotting here. I'm plotting this COCO. So I've solved this problem with these constraints on my f and on my g. I've plotted the transform points, and they have really strong linear correlation. They're very dependent. Okay, so how on earth do I compute this thing? It seems pretty hard. I've got two functions, each of infinitely many features. Let's see what happens, okay? So first of all, in terms of interpretation, like here is my constraint covariance, right? I've got my constraint here, my unit ball constraint, which I've got here, and my covariance between functions of features of x here and functions of features of y here, okay? So this is what I'm computing. Now, my features, I've got infinitely many features of x and of y, so that's rather challenging, but let's understand what this means, okay? Bear in mind also, this tilde notation means that I've centered my features, okay? So here I'm taking the covariance between features of x and of y. Well, the covariance is basically like the expectation of f minus its mean times g minus its mean. So what I'm doing here is I'm compressing that notation by just centering my features. If I have 0 mean features, then I don't have to subtract the mean of linear combinations of those features. So I'm replacing covariance with expectation, and I'm centering my features. I'm removing the feature means. Okay, so now I've got the expectation of a product of centered features of x, right here in blue, and centered features of y, here in red. Okay, so let's write this now in matrix form. Okay, I've got the expectation of the product of f of x, g of y. This is this vector of coefficients that define f. Then the expectation of the outer product of the features of x and of y times the vector of coefficients g. So I've just taken the expectation inside because these features, these coefficients f, of course, aren't random variables. They don't have an x in them. So what you can see now is you've got basically f transpose, gigantic matrix of infinite size, vector g. This matrix, each of the entries is a product of one of the features of x and one of the features of y. So in a sense, I'm saying, here is my dictionary of features of x, here is my dictionary of features of y. I take every single pair of features that I can define, I make a matrix of those pairs of features, I take the expectation, that's the expected covariance of all my centered features of x's and y's. It's an infinitely big matrix, that's a problem, but this is what I'm doing. And then, I've got this matrix of covariances between all of these pairs of features. But I need a summary statistic of that. And this is what, hitting it from each side by a vector f and g does. It takes that huge matrix and it gives me a number. That number is the largest singular value of a matrix, right? The reason is these have norm less than or equal to 1. So if you remember, the largest singular value of a matrix is a vector with norm less than or equal to 1, matrix, vector norm less than or equal to 1, and I find the two vectors that maximize that product. So this is my summary statistic of this huge matrix. It's the largest singular value. If all of the covariances are 0, the largest singular value is 0. So this is very convenient. Okay, so what is my COCO? My COCO is my largest singular value of this covariance, this massive covariance between every pair of features. So in this sense, you can sort of understand why it is that it's able to find every kind of dependence. If my dictionaries of features are rich enough, I've got this matrix of covariances between all of these features. If they're rich enough, I'm confident that I have independence. Or I'm able to prove, in fact, that I have independence. Okay, so I can write this down, but I need to compute it at some point. All right, how do I solve this thing? Okay, let's say I've got samples. I've got x and y like I did in my slides a couple of slides ago. And I want to find these functions. So clearly I was able to because I plotted them, but how do I do it? It turns out that this is the eigenvalue problem that you can solve to get these functions. Okay, I'm going to show you the form of this problem, and then I'm going to show you where all the bits come from. But this is first of all to convince you that even though I'm finding the largest singular value of an infinite dimensional matrix, I can do this on a computer at a cost which is cubic in the number of samples that I've seen. So here is a generalized eigenvalue problem that is solving this. What does it contain? It contains the product of k and L. K is the matrix of similarities between my x's. L is the matrix of similarities between my y's. I've put these tildes on top because I'm computing these kernels on data that's been centered. Remember when we turned the covariance into an expectation, we had to remove the means. So I'm removing the means of my features in feature space, and then I'm computing the kernels. So that's just a little bit of algebra for you. So this eigenvalue problem is in terms of my kernels on my x's, my kernel on my y, and that's it. The gamma here is my constraint covariance. So this is my empirical estimate of my largest singular value of this thing. Okay, how do I get my functions? Well, here is my function on x, okay? It's a weighted sum of kernels on my samples that I've observed and on the x that I'm evaluating at, minus this mean term. because I've subtracted my means in feature space. So these alphas that I get as the eigenfunctions of this eigenvalue problem, I can then use to plot my f's, which is what I did a couple of slides ago. So this is to show you that, even though I'm dealing with these infinite matrices of features, if I compute the constraint covariance on finite data, I get a simple problem that I can solve. So I'm next going to show you where all of the parts of this thing come from, so it's not like a mystery. Okay? This is my Lagrangian for my constraint covariance. So what you can see on the top line here, this is the covariance between f of x minus its mean and g of y minus its mean, or the expectation of that product, okay, which is the covariance. And then I've got my constraints here, second line, smoothness constraints. So this is saying, that my norm of f should be less than or equal to 1, and my norm of g should be less than or equal to 1. Because remember, I'm maximizing the covariance between f and g subject to some constraints, so they should be smooth. All right. So I'm going to assume that f, my solution, is a sum of centered features of x, and g is a sum of centered features of y. So in a sense, this seems to be a little bit of a shortcut, but it's not a stupid shortcut. The reason for that is that if you look at the first term, the covariance, you can see that this is a covariance of centered features of x and centered features of y. So in a sense, if I had f orthogonal to these centered features, it wouldn't affect the first term at all. And then these second terms, if I included any f orthogonal to the span of my features of x, then that would just hurt me in this bound, because I would have to pay for the fact that I'm using extra f away from my features of x, but I'm not gaining anything from it because my first term doesn't change. So this, at a high level, is called the representer theorem, but the idea is actually a simple one. It's just to know that these f's and g's are going to be sums of my features of my observations, because anything else would just sort of waste capacity and not give me any benefit. Okay, so let's say that my f is my weighted sum of centered features of x, my g is my weighted sum of features of y. You can already see appearing here the alpha and beta that I had on my previous slide. So this is already telling me that I'm on the right track. Okay, let's first look at what happens to these constraint terms. So the constraint terms, this is the norm of f squared, right? My norm of f squared is less than or equal to 1. F is a weighted sum of my centered features of x. That's what I have here. The norm of f squared is the dot product of this with itself. And so now I just notice that, well, I've got the dot product of this in itself. That means I've got a whole bunch of centered features of x dot producted with centered features of x. If I write this in matrix form, I just get the next expression, where I've got alpha transpose and then my k, which is the matrix of pairwise dot products of centered features of x and centered features of x, and alpha. So this is my matrix expression for this term. Are there questions about what I did here? Okay. So this is the first term that I had. The second term is a little bit messier. So this is probably the messiest slide in this presentation. So just hold on. Here is my covariance. This is my covariance, which is the expected product of centered features of x, or the functions of centered features of x, and functions of centered features of y. So this is my covariance between f of x and g of y. Now we plug in our definition of f, right? Remember that we said that our f was a weighted sum of centered features of x. So I plug this in here, and now I notice that I'm getting a kernel between centered features of x and centered features of x. And here I didn't show it because I didn't want to make my slides like a huge mess, but I'm getting the same thing here. I'm going to get a kernel between centered features of y and centered features of y. So here I've got a product of kernels on x and kernels on y with these coefficients alpha, and for g I've got coefficients beta. And when I carry that through, then I just get my alpha transpose KL beta. So you'll notice that I've recovered two terms here. My first term I've recovered has alpha K alpha. I've got here alpha transpose KL beta. So let's go back a couple of slides. This KL comes from the covariance. The K on the diagonal here comes from the norm of F term, this term here, and then the L comes from the norm of G, so this term here. So you can, I haven't done the whole proof, but you can see where all of the terms come from in this generalized eigenvalue problem. And you can see that in writing this generalized eigenvalue problem, I've got rid of all of the infinitely long feature vectors and expressed everything in terms of kernels, which I can then compute. So are there questions? Okay. So this was the most, I think, mathematical side for the talk, so you've survived that. So now I will show a little bit more what this constraint covariance means. Okay? So I have a measure of dependence. What I'm interested now in understanding is, like, when is it big, when is it small? Like, what are the properties of data that give me a big covariance, a big constraint covariance? What are the properties of data that give me a small constraint covariance? And this is what I'm going to illustrate now with some nice examples. So here I've constructed a really, I think, informative toy example of data which is dependent. The joint density of x and y is a product of sinusoids of x and of y, with a frequency omega. And as this frequency increases, the dependence occurs at higher and higher frequencies. So here's an illustration. Here, omega equals 1, right? So I've got a very simple contour plot here, where I've got low density regions off on the diagonal and high density regions off the diagonal. If I draw samples from this, I get something looking like that. Here is a rough density. So here, like, the high and low density regions are really interleaved at a very high frequency. If I draw samples, I get something like this. So this is the family of densities that I'm going to be using. And I'm going to be computing the constraint covariance as omega increases. Okay? So here is the simplest case. Omega equals 1. Remember, I've got, like, off my diagonals, I've got very few points. On my diagonals, I've got very few points. Off my diagonals, I've got lots of points. Here are my smooth functions that I get when I compute constraint covariance. And here is the transform points. So in this case, my smooth functions are pushing my points into the corners, which will give me a high linear correlation. And my constraint covariance is 0.09. Okay, so these are dependent points. I've transformed them to make them even more dependent. It's working. Okay, now let's double the frequency. So now you see a sort of checkerboard pattern. It's going to be, here it's low, high, and then that pattern sort of interleaves. So this is a harder dependence to find. My F and G now oscillate at double the frequency that they did before. So they sort of, they're going down, up, down, up. The transform variables, again, like these functions push all the points into the corners, and again, my correlation is high. But you'll notice that my constraint covariance has gone down a bit. It's now 0.07 rather than 0.09. So remember that we have required our functions to be smooth. We've asked ourselves, can I find smooth mappings of x and y that maximize their covariance? Well, here my functions are less smooth, so the covariance that I can achieve is going to drop because the smoothness constraint sort of damages my capacity for moving the points around to maximize my covariance. Let's continue. So now omega equals 3. My transforming functions f and g now oscillate 3 times. And I can still transform my points, but now my constraint covariance, my COCO, has gone down to 0.04. So my dependence is dropping. Because my functions are getting less smooth, I've got less ability to move my points around. Here's 4. Here my COCO is now 0.02. It's even harder. Now I have to oscillate 4 times, but I can't really do it because my functions have to be smooth, so it's struggling a bit here. Does anyone want to guess what omega is here? Zero. So basically, the weird thing about the 0 is it gives me the exact same constraint covariance as 4. So this is another illustration of bias, because what I've noticed is that I've got some limited number of points. and I'm moving them around using a smooth function, and it turns out I can, because I've got 200 points, I can sort of move them around a bit to give me some sort of residual dependence. But the dependence that I get for completely independent variables is the same as the dependence I get for very high frequency interleaved variables. Now, as I see more samples, I will, sort of, in a sense, nail down my functions more and more. So this bias is going to drop. But, for, I think it's 500 samples, which I've got here, the bias is present and is visible. And so the number that I get, my constraint covariance, is not going to be 0, even though the variables are independent. It's going to be biased above 0, because I'm sort of shifting my points around to get some sort of dependence. Yep. Very good question. So then the question is this biased value of Coco should not be statistically significant, right? Because it's the kind of value I would expect to see when X and Y are independent. So I'm going to shortly talk about how to find the dependence threshold. That's a very good question. Yeah. And indeed, this Coco is not statistically significant. It's, this is chance level. And that means that I cannot detect this dependence here with the number of samples I've seen. I would need more samples before I could see that. Are there more questions about this? Yep. So how did I... Oh, I mean, the uniformly sampled points, here I'm just making uniform minus 3, 3, minus 3, 3. So I'm generating X uniformly on an interval, Y uniformly on an interval, and that's it. Yeah, so they're completely independent of each other. Here I'm just doing rejection sampling to generate these sinusoidal ones. But then uniform is just uniform. So 0 dependence, yeah. Any other questions? Okay. So so what we've seen is that what is more dependent and less dependent according to Coco? Well, more dependent is that the dependence exists at low frequencies. So if X and Y are dependent and this dependence occurs, at low frequencies, which is to say that smooth functions can easily reveal it, then my Coco is going to be big. If the dependence occurs at high frequencies, so smooth functions can't easily reveal it, then my Coco is going to be small. So this sort of tells me, what's an easy problem, what's a hard problem. And this, I think, conforms to what we as humans would consider easy and hard. If I see a plot like this with my X and my Y, visually I can't see a whole lot of dependence in that. I would need to see way more samples before I would see a checkerboard pattern. And this is what my constraint covariance is giving me. It's sort of ordering my dependence so that this is less dependent than this, which I think is reasonable. All right. And what we've noticed is this bias problem. So even for independent variables, Coco will not be 0 at finite sample sizes. There is going to be a bias, which will decrease as the samples increase. And that's just because, with finitely many points, I can shift them around a little bit to give myself some small amount of dependence, even if there's no dependence to start with. But it won't be significant. Okay. So the next question is, here's Coco. Can I do better? All right. So here is an example. I've got my X and Y variables here. They're dependent. They're not correlated. I've transformed X using a smooth function, transformed Y using a smooth function. Suddenly, my correlation's gone up to 0.8. It's very significant. I've found a dependence. But, have I done everything I can do, or could there be dependence that I've missed? So remember what we said that Coco was. Coco was the largest singular value of my matrix of covariances between my features, my centered features. So what if I use the second largest singular value and the second largest singular functions? I mean, I can. So here are the second largest singular functions of this covariance. I've just computed those using the second largest eigenvalue from that eigenvalue problem I showed earlier. Here are my points. So the correlation here is still significant. It's not as good. And my second Coco is lower than my first Coco. My first Coco was 0.1. My second Coco was 0.06. But it's still there. There is dependence that we've captured using the second largest singular values that we've missed using the largest. So this is a mode of dependence that I might also be interested in. Like I've said, here are my functions that transform my data to have high linear correlation, but there are functions that are orthogonal to these first functions, because they're orthogonal, right? And that also has a significant correlation. So this mode of dependence is also interesting. Maybe a bit less interesting, but it's still there. Right? And then I can continue. I can say, third, fourth, fifth, etc. So I could use the whole spectrum of my solutions of my eigenvalue problem, and I could, have a whole bunch of dependence statistics. The largest one, second largest one, third largest one, and so on. So what if I wanted to summarize all of these statistics into a single number? So one way to do it would be to take the sum of the squared singular values, right? So I take my first COCO, second COCO, third COCO, I take the sum of the squared COCOs, and that gives me a dependence criterion. So the sum of the squared singular values is called the Hilbert-Schmidt norm. So this statistic is called the Hilbert-Schmidt independence criterion. And that's a more complete measure of the dependence because it's taken into account all of the modes of dependence that you have, the first, second, third, and fourth, etc. Okay, so now here's the surprise. This is actually the MMD between joint and product of marginals using the product kernel. So if you wondered where the start of my lecture came from, this is where it came from. So this justifies using the MMD with the product of kernels because when I'm doing that, I actually know what I'm doing. I'm taking the sum of the singular values squared of my covariance of my features. So it's actually a pretty sensible measure of dependence. And if somebody then asks you, well, what is the dependence that I found here? I can plot these two leading functions, my two largest singular functions, and I can say, well, this is the most important mode of the dependence that I found using this statistic. So I can show people why things are dependent. I don't just assert that they are dependent. Okay. So a question that we had earlier is, I've computed this statistic, but I've seen that the statistic, may have some bias, right? It turns out, actually, I should mention that for HSIC, it's possible to compute an unbiased estimator of this quantity. You just have to add and subtract some centering terms. So this is quite nice, even though you cannot compute an unbiased estimate of COCO, unfortunately. So that's a kind of pleasant consequence of using HSIC instead of COCO. All right, but we now have a measure of dependence. We've got our samples, we've computed HSIC, and we want to say, is HSIC statistically significant? So is it large enough that it's unlikely to be due to chance when the variables really are independent? All right, we've said that the HSIC, or the MMD between joint and product of marginals, is the trace of the product of the kernels on my x's and the kernels on my y's. So with appropriate centering. Okay, so, I'm talking the language of statistical testing, so just to remind everyone from yesterday, what we want is a threshold such that if it were really true that x and y were independent, then I would exceed this threshold, like I would have a large HSIC with small probability. And that probability is something that I choose as a user, so I'm saying 95% of the time if x and y are independent, I want to be below threshold. 5% of the time if x and y are independent, I'm prepared to make an error and get a false positive. And I choose, as a user, how many false positives I'm prepared to tolerate. So here is the bad news. If you remember from MMD, the distribution, the values of the MMD that we would expect to see under the null had a very horrible form, right? This infinite weighted sum of chi-squareds. And it turns out that the bad news continues for HSIC, because it's a form of MMD. If it's really true that x and y are independent, I again get as a distribution of HSIC, like the HSICs that I expect to see when it's really true that x and y are independent, is going to have this horrible form as well. The form is even worse than it was for MMD. This is why I've put it in really small font here. So it's just there to scare you. It's not there to be read. Okay, so what on earth do I do to get this threshold? Okay, so if you remember what we did for MMD, we found a permutation approach to get the threshold, and that's the approach we're also going to take for HSIC. Okay, so given that it's really true that pxy is equal to px times py, what is the threshold such that the probability of exceeding this threshold is small when it's really true that x and y are independent? So my permutation in this case is going to be to simulate from my data the case that x and y are independent. Okay, so here is my original time series. I've got x1, y1, x2, y2, x3, y3, and so on. Now, the permutation is really the obvious one. I've already hinted at it before. I just take my x1 and I make a random y attached to it, x1, y7, okay? x2, y3, x3, y9, x4, y2, etc. So now I've simulated from the case where there really is no dependence between x and y. Like I've taken my picture of my animal and I've made a random caption attached to it. This will give me a sample of HSIC in the event that x and y are independent. And then I scramble my data again, and I compute another HSIC. Scramble it again, compute another HSIC. So this is what I'm doing now. And then I get a histogram of the kind of HSICs that I would expect to see if x and y were independent, and then I use the quantile of that for my test threshold. So I have a typical set of values of HSIC for when x and y are independent. If my real HSIC is way, way above those, I'm confident that there is a dependence. If the HSIC I observe is within that set of samples, then I'm confident that my variables are independent. Are there questions about this permutation approach? All right, so now let's see how it's going to work. So this is a kind of cool example of a problem. Here I've got text in English and text in French. So x1 is a little fragment of English text, x2, y1 is a fragment of French text, and I'm seeing this repeated over and over. Okay, so what I've done, I've got this like large text in English and French. I've fragmented it into pairs, and then I'm asking whether the English and French text are translations one of the other. But I want to solve this problem without speaking English or French or knowing how to translate. All right. So let's see now what happens if I'm in this setting and I'm using HSIC to find the dependence between x and y. So here is my matrix K on pairs of the English fragments. So each little square that you see in this matrix here, this K matrix, which I've got here, anyway, yep. Each of these little squares is how similar one extract of English is to another extract of English. So going back to the previous slide, I'm saying how similar, for instance, this is to this, like the first one to the second one. And then first one to third, first to fourth, second to third, second to fourth, etc. And then I get this matrix K, which is a matrix of similarities of each English extract to another English extract. And I do the same for my French. So I have a separate matrix of how similar each French extract is to another French extract. And now if you squint at these matrices, you're going to notice that the pattern is very, very similar, because indeed the English and French text are translations one of the other. So if I take the matrix dot product, so the trace of the product of one matrix with the other, with appropriate centering, then I'm going to get a big number, because these matrices are similar. And so I'm concluding that the English and French text are translations. So a question you might have now is like, what is the kernel that I used here? So the kernel that I used is something called a K-spectrum kernel. What it does is it counts the number of matching substrings in one extract and another extract. So if I have like substrings of increasing length and they match, I get a strong matching score. It also allows for things like wildcards and approximate matches. But the important thing is that I never have to compute similarity between English and French. I do everything within a language. So this K matrix is only similarity of English to English. L matrix is only similarity of French to French. I never have to translate one to the other. And yet I can find that they're dependent. And indeed, like my type 2 error, the probability of false negatives, is actually 0 for this problem. So with enough data, I'm able to find that the translations are translations one of the other. A more primitive kernel is something called a bag of words kernel, where you just count the words that match. As you might guess from these little short extracts, counting the words that match isn't very good. And then your type 2 error is a lot higher. So I've got 20% false negatives. I've missed quite a few of my dependencies. Okay, so that's the story for testing dependence using kernels. Are there questions about this before I go on? Yep. Mm-hmm. Yep. Right, so optimizing kernels mattered, and optimizing kernels still matters. So think of our smooth functions here, right? If I chose functions to be too smooth, I wouldn't find anything. If I chose functions to be crazy rough, then everything would be dependent. So I do need to actually find a trade-off between these two. So I didn't mention it in this talk, but you can do exactly the trick that we did for MMD. We can maximize the signal to noise, the ratio of the statistic to its variance, over the choice of now two kernels, one for x, one for y. If we do that, we get a test with a lot of power. Yeah. Yeah, so same trick applies. Are there any other questions? Yep. Mhm. Yeah, so in fact, you can use this for feature extraction. So let's say that my y's are some sort of labeling or something that I want features to be predictive of, and then my x's are, whatever I'm trying to predict from. I could find functions of my x's that are very predictive of my y's, and I could use these as features. I could even use HSIC to find which dimensions of my x are most dependent on my y's, because I can, for different input dimensions, I can find the ones with the biggest HSIC. For feature selection, we've done that actually. We had a JMLR paper in 2012 where we used HSIC for feature extraction. What we haven't done, which would be interesting, would be to use these sort of nonlinear features, like the maximum singular function or the top 5 singular functions as features. But these are valid approaches. Yeah. Any other questions? Okay. Actually, what is my time? Because that will determine what I do next. 10 minutes? 7 to 10 minutes. Okay. So in that case, I'm not going to talk about model selection. I'm going to talk about something else, which is, where is it? Here we go. Testing higher order interactions, because this is something I can fit into 7 to 10 minutes. Yeah. So I have talked about testing statistical dependence. And that's dependence between two variables. What happens when we have more than two variables? So fortunately, like you've already heard a lot about causality, so what I'm going to tell you now, I think might be quite interesting. Okay, so here is a graphical model containing 3 variables. And what I've got now is 2 parent variables, x and y, influencing a child variable z. All right, and I'm making observations from life, and I'm trying to figure out whether this V structure exists, so whether I've got 2 independent parents having an effect on a child. Now, the interesting case, from my perspective, is the case where individually the influences are weak, but the combined influence is strong. So if individually these influences were strong, then in a sense, like, I wouldn't have to worry about the combined effect, right? Because I could find these individual edges very easily. I could see, X has a big effect on Z, Y has a big effect on Z. I know these edges exist. But here is a nice example of a case where the individual effects are weak, but the combined effect is strong. So let's say I have some, reagent, some chemical compound, and I apply heat to it, and some reaction starts to happen, but not very fast. If I apply a catalyst to it on its own, a reaction starts to happen, but not very fast. If I apply heat and a catalyst together, I get an explosion. So obviously, individually, these 2 influences are weak, but if I combine the heat and the catalyst, I get a strong reaction. And this, individually weak but strong combined effects, these are the ones that are really interesting to detect, because I can't detect these influences using just pairwise dependence on its own. All right, so this is my cartoon. Here I'm going to generate data with the properties that I've described. Okay, so this is a sort of extreme case where x is actually independent of z on its own, y is independent of z on its own, but the combined effect exists. People who are rigorous about graphical models will then criticize this because I've not been faithful, in the sense that I shouldn't be able to draw an edge unless it exists sort of on its own. So what I would do to modify this to make it faithful would be to add a little weak link between x and z and a little weak link between y and z, so these edges exist in isolation, but the combined effect is strong. So that's a technicality. Let's look at how I've generated this data. So x and y are just IID Gaussian. Very boring, but they're independent. Okay? And z given x and y is a sign of their product, scaling some exponentially distributed variable. Okay? So x and y are independent, of course, by design. That's this like top left thing here. Y and z, though, are independent in isolation. X and z are independent in isolation, but x times y is extremely dependent on z. Okay? So, in isolation, x and y can't demonstrate dependence on z, but together they have a strong dependence. And this is what we're trying to detect. All right. So let's assume that we've established already before we start that our parents are independent. Then, given that our parents are independent, we can conclude that the V structure exists if the parents become dependent conditioned on my Z. Okay? So, to illustrate, if I've observed an explosion, I know that there must have been heat and catalyst, right? So suddenly I've induced a dependence between my parents because I've seen that an explosion happened. Okay? So, given independent parents, then if the parents become dependent when I condition on my explosion, then I know I've got the V structure. Or I could do something else. I could say that, like, if I can't factorize my model in any way, I know a V structure exists. So if I can't say that I can break x and y off from z, or x and z off from y, or y and z off from x, if I can do none of those things, then I know that there must be links from x to z and y to z, and hence I know I must have dependence. So I can do, I can check all of these pairs of correlations, and if I reject the null for all of them, then I have dependence. So these two approaches I can take. Let's see how well they work. So the bad news is they don't work very well. What I'm going to do here is I'm going to take my distribution from a couple of slides ago, and I'm going to add junk dimensions, so dimensions full of noise. The reason I'm adding dimensions full of noise is just to make my problem steadily harder. So on my x-axis here, I'm adding more junk dimensions. On my y-axis, I've got the fraction of the times that I get a false negative. And what you'll notice is that as I add more junk dimensions, using either the conditional dependence approach or the 3 pairwise dependence approach, the fraction of false negatives goes up to 1 very fast. It's a hard problem. I'm in a rather tough situation. So the question is, can I solve this problem? Is there a better way to do it than these two approaches, which seem to suffer quite a bit when my dimension increases? So the way that I'm going to approach it is by thinking of how I might generalize HSIC to more than 2 variables. So here is the way I could generalize it. Remember, what HSIC is doing. It's looking at the difference between the joint and the product of the marginals, as I've done here. Okay? So if I have 3 variables, what does a sort of measure of factorization look like? So here is a proposed measure of factorization. And it's kind of messy. I've got the joint minus px pyz minus py pxz, etc., etc. So what does this mean? And why might it be a good candidate? Let's look at it graphically. So what is this, what is this delta L of p? First I have my joint distribution, that's here. Then I subtract off the case where I'm breaking x from yz. So I'm breaking off x, and I've just got yz left. Here I'm breaking off y, and I've got xz left. Here I'm breaking off z, I've got xy, and then I add 2 times the product of all of them. Okay, so this is graphically what I'm doing. So why might that be a measure of whether there exists a factorization? Well, let's assume that the truth is that x really is independent of y and z. So in that case, the first 2 terms cancel. The first term is my true joint, but I know that x is independent of y and z. And the second case is a case where I mandate that x is independent of y of z. So these are obviously going to cancel because they're the same thing. But then everything else cancels too, because if I know that the truth is that x is broken off y and z, then the last 3 terms are just px times py times pz. And they all go away. So this means that, if a factorization exists, then all my terms cancel. So if I can break pxyz into px times pyz, everything cancels. If I can break it into py times pxz, everything cancels. If a factorization exists, this thing will be 0. In this case, this is the sense in which it generalizes this example here, where d equals 2. and there is only one factorization that I care about. Okay, so, if any factorization exists, 2 minutes, that's fine, So if any factorization exists, this implies that this is 0. What might be missed? Well, actually, the implication in the other direction doesn't work. I can create variables which are completely coupled, and yet this statistic is going to be 0. They're coupled in a really pathological way, in just the right way that I make this thing 0. So here's an example with binary variables where everything is dependent on everything else, and yet my statistic is 0. So basically, my statistic sort of works only in one direction. If it's not 0, I can be guaranteed no factorization exists. If it is 0, then all bets are off, and I may be in one of these crazy cases. I hope not, but, bad luck. All right. So now I have this statistic. So the good news is that if my statistic is not 0, then I can reject the null. If the statistic is 0, then I can't say anything. Now, my next thing is, well, with the statistic here, I computed the MMD using the product kernel, and I got a nice statistic. What if I computed MMD using the product kernel, now a product of 3 kernels, on this crazy expression? Well, unfortunately, if I do that, here are all of the terms that I get. I get all of these cross terms. And these cross terms are in terms of my K matrix on my X's, my L matrix on my Y's, and my M matrix on my Z's. So you might think this is going to be a real pain to implement, but the good news is everything collapses down, and I get something that looks almost like MMD. So this first term here, K times L, this is just the MMD term with the product kernel. I've written it in a slightly different way with this ++ notation, but that amounts to taking, the trace of the matrix product as I had done before. But now I've got a third term, which is my Z variable, and this is this M term here. So good news is it's as easy to compute as MMD. Are there questions? Okay, so this is my statistic for 3 variables, and quite remarkably, this works way, way better than the other 2 approaches we tried. So it's failing to detect that there is a V structure much less of the time, even when I've made my problem hard by adding lots of nasty noise dimensions to it. So, if you're looking for these V structures, this is an approach that I can recommend to take, because it's able to find them, I think, in a more reliable way than conditional independence tests, than, just looking at individual pairwise tests. Particularly in the case where we've got this really strong interaction that you can't detect using the individual edges alone. So what about d equals 4? We've done 3, so 4 must be easy, right? So this is a nasty mathematical expression which captures for 4 variables what we did here in graphical form for 3 variables. This is a way of looking at all of the ways we can break 4 variables into subsets such that the distribution factorizes over those subsets. The bad news is that the number of terms is gigantic, and unfortunately, the expression doesn't collapse as it did for 3 variables. So for 3 variables, everything cancelled, we got a simple expression. For 4 or more variables, you have to keep track of everything. And the size of everything grows extremely fast. So this is a plot from Wikipedia where the dimension goes up. This is the number of ways in which you can break these into factors, and the number of terms just blows up. So if you have 4 or more variables, the answer is don't ask whether any interaction exists. You need to ask a more specific question, does this variable have coupling with all of the others, or something like that. But you can't just say, is there any factorization at all, because that question is too general to answer here. All right, so I think this is a good place to stop. So here are my co-authors. These are my co-authors from Gatsby, so my students, and these are collaborators that I've worked with for all of this work. So I encourage you to look at the papers. All the software is online. And this is Kernel beer, so thank you.